Ayan. So, for this video, we'll discuss the unit normal vector and the binomial vectors and basically the applications of binomial vectors, which are the normal planes and the oscillating planes and the torsion. So, the definition of a unit normal vector is that it will be perpendicular to your unit tangent vector. No? So, your unit tangent vector, as you can see, it has the same formula or similar formula for a tangent vector. This is equal to r prime of t over the length of your r prime of t. So if you have to find uh, your vector that is tangent to this, then this will be your formula, ano? And if you want to find a normal vector, it will be tangent to this, or in some way the function of this t, okay, will be similar to this. So what is a unit vector? Sorry, unit normal vector. A unit normal vector is again a normal a vector that is perpendicular or orthogonal to your unit tangent vector. So you have this as your formula. Now we have also another vector that is both tangent to, or both not tangent, but both orthogonal to your unit tangent vector and your unit normal vector. That is your binormal vector. So as you can see, how do we derive for the binormal vector? So to find this binormal vector, will be just a cross product. No, if this is your angle in between, then the binormal vector is just, or actually this two vectors lies on the same plane. Then your plane will have a normal vector of the binormal vector. So therefore again, it will be just a cross product of these two vectors, the unit tangent vector and the normal vector. Okay, so find the unit normal and binomial vectors of the circular helix. Actually, this is from previous example, no? Just to be more efficient, so this is from the example previously, no? Now, how do we find the unit normal vector? So the unit normal vector, we have n of t. This is equal to the unit tangent vectors derivative over the length of the unit tangent vectors derivative. So did we already solve for this? Did we? I think so, no? Okay, we already solved for this. No, not this pala. Let's check on that. Oh, we did not solve for this. Again. Um, wait. No? Or from the previous topic. Um, let's just check. Okay, we haven't solved for it. Okay, we did not solve for that yet. Okay, let's solve for this. Ano? Okay, let's go for it. Yeah. So for this given problem, so we want to solve first for the unit tangent vector. So the unit tangent vector is equal to r of t, or r prime of t over the length of r prime of t. So what is r prime of t? So r prime of t, this one I remember solving already. So this is negative sine t plus cosine t. So don't forget the unit vectors, and then plus k. And then the length of this, we have the length of this r prime of t. This is equal to, we have the square root of negative sine t squared plus cosine t squared plus 1. So as you can see, this will be equal to 1. So this the solution for this is, this will be the square root of 2. So we have this, the unit tangent vector will be equal to, sorry, I forget already the writing of the vector, no? So this will be equal to the negative sine t, okay, I hat plus cosine t j hat. plus k hat, and then all over square root of 2. Where is it? Sorry. Sorry. Where is it? So over square root of 2. Ayan. Okay. So therefore, this is it, no? So we have we can just factor out the square root of 2. So we have 1 over square root of 2 times negative sine t I hat plus cosine t, and then j hat plus k hat. So this is your unit tangent vector. Now, what we all need to do is to find the first derivative of your unit tangent vector. So for the first derivative, okay, so we factor out the constant. It's okay. We can just find the derivative of this independently. So we have here 1 over square root of 2 still. So the derivative of this is negative cosine t I hat, and then we have negative sine t j hat, and then this will be 0k. Ano? So you may not write 0k anyways, but I'll just write here 0k for now. So we're good for this, no? So this will be your first derivative of this unit tangent vector. Now to find the length. So to find the length, you just find the square, no, of the sum of the squares. So this point you have to include this 1 over square root of 2, right? You have to include this, right? So I guess we have to really distribute this one, no? So we have negative cos t, and then over square root of 2 I hat, minus we have sine t over square root of 2 j hat plus 0k, or we just remove the 0 now for now. So to find the length, this will be equal to the square root of the sum of the squares. So negative cos t over square root of 2 squared, plus we have negative sine t over 2 squared. Yeah. So as you can see, we have again, so this will be square root. We have again another scenario wherein this will become what? No? Cos squared plus sine squared. So this will be cos squared t plus sine squared t. And then since this is over 2, no? The square root of 2 is 2, then we can combine this into 1, right? So combine this into 1, and then we can find the square root of this independently to solve for its square root. So this will be equal to the square root of, we know that this is 1, and then over the square root of 2. So this will be equal to 1 over the square root of 2, or you can write this as square root of 2 over 2. Okay, now to find the unit, normal vector, this will be equal to t prime of t, which is this, and then the length of t prime of t. So we have negative cosine t over the square root of 2 I hat minus sine t over square root of 2 j hat divided by 1 over the square root of 2. Okay, so 1 over the square root of 2. So actually you can cancel this out. So therefore your unit normal vector, not no prime here, sorry, but there should be a vector. So n of t is equal to negative cos t I hat minus sine t j hat. So this will be your unit normal vector. Although this can be further expanded, no, you can include 0. Actually, 0 is included here. So let me just rewrite this one. But it is equivalent, no? So we have negative, or we can write this as in this form as well. In this form as well, ano? So negative sine t, negative cos t, negative cos t first, and then negative sine t and 0. Yan. Okay, so you can write this also in this form. It is virtually the same. Now to find the binomial vector, this is the cross product of your, which one is first, the tangent vector or the normal vector? So the tangent vector first, and then the normal vector. The normal vector. Okay, so what is this? What is the tangent vector? We have this. Okay, right? So we have 1 over square root of 2, or we can just distribute this, no? So we have negative sine t over square root of 2 I hat, and then minus plus cosine t over the square root of 2 j hat, and then plus 1 over square root of 2 k hat. Yeah. Okay. And then this is multiplied or cross multiplied by the normal vector that is negative cos t I hat, and then negative sine t j hat. So this will be plus or minus j hat, and then we have 0 now. So we can just write this down as 0 or whatever you like. No? So basically this is 0. Okay, now how do we perform the cross product? We can create a determinant of this two. So make this larger. So we have I, we have j, and then we have k. So the first one is tangent. The tangent vector, so this will be negative sine t over square root of 2, cosine t over square root of 2, and then 1 over square root of 2. Negative cos t, we have negative sine t, and then 0. So how do we perform this the crisscross method of crisscross rule? So we have here 0, and then tracing this, no, and then this, we have minus negative sine t over the square root of 2, and then we have I hat, and then plus, so for the j term, we have this, and then extends to this, we have 1 over square root of 2, sorry, not, we have negative cosine t over square root of 2, and then we have this, and then this, so 0, so minus 0, and then for k, so for k, trace this out, we have this, so this will be, sorry, we have here j at plus, this will become positive, no? So we have sine squared t over the square root of 2, right? And then what's next? So minus this. So minus negative cosine squared t over the square root of 2n. And then k hat. Simplifying this, we have sine t over square root of 2. And then I hat. And then this will be negative, no? Negative cos t over square root of 2 j hat. And then this one can be actually simplified. This will become positive, right? And then the square root of 2 can be factored out. So we have this will become 1 over square root of 2. Why can't I erase? 1 over square root of 2 multiplied by sine squared t plus cosine squared t. And we know that this is equal to 1. So this will be just 1 over the square root of 2, right? 1 over square root of 2, and then k hat. So this will be your binormal vector. Okay, you can write it in this form, or you can factor out this. We have, let's say, this is also the same as we have 1 over the square root of 2, and we can also write this as sine t, and then negative cos t, then 1. So we can write this in different forms. Yeah. Okay, so that's it for this example. Okay, now let's discuss about the oscillating plane and normal plane. So what is the oscillating plane? So the oscillating plane is a plane that is perpendicular to the binormal vector. So remember that the oscillating plane osculating, sorry, not oscillating, osculating plane normal to the binormal vector, and then the normal plane, okay, is normal to the unit tangent vector. Yeah, so this is what you need to remember. No? Okay, so we're already familiar with planes, so this will be a little bit easier. So find the equation of the normal plane and the oscillating plane at the point P0, 1, 5, or 2. Okay, so how do we find the oscillating plane? So for the equation of a plane, how do we describe an oscillating a plane, no? So for a given plane, the given formula for a plane is we have a and then x minus x naught plus we have y, sorry, but b and then y minus y naught plus c z minus z naught and then equals to 0, right? So this is the equation of a plane, no? Plane. Okay, now how do we do this? So we have this as our initial point. So basically this is your x naught, y naught, and z naught already. Okay. So what do we need here? A, B, and C. So what is A, B, and C? So A, B, and C, I'll just write this down here now, sorry. But A, B, and C is your normal vector, if you can remember. So therefore, we have to figure out what is the coefficients of your normal vector. So we already solved for this now, but what is the oscillating plane? For the oscillating plane, you can remember, this is normal to binormal vector, right? So therefore, your normal vector here, actually we have the same problem as the last one. So we already solved for the binormal vector, which is this, or this one. So therefore, we know that this is your A, B, and C, right? So your normal vector is, we have sine t over the square root of 2, okay? And then we have negative cosine t over the square root of 2, and then 1 over the square root of 2, right? So therefore, to describe this, so this will be your A, this is your B, this is your C. So using this formula, the equation of a plane, this will become, we have sine, sorry, no, it should be at what point? At this point. So we also want to figure out pala yung point of interest. What is the value of t? You know? So we have this as our b of t, or the binormal vector of t, but we do not have a value of t yet. So we have to substitute this t that is incorporated with this point. So when will be cosine t equal to 0? No? When will sine t be equal to 1, and so on. So t is equal to, actually t is just equal to 5 or 2 based on this. So we know that t is pi over 2 based on this relationship and this one. Therefore, we have b prime of pi over 2, which is also your normal vector at this point, is equal to, we have, what is sine pi over 2? So sine pi over 2 is 1. So we have 1 over square root of 2. What is negative cosine pi over 2? So negative cosine pi over 2 is 0. So we have 0 here. And then what's next? Ah, sorry. I think I got something wrong. And then I didn't do something wrong. And then the last one, sorry, this will be 1 over square root of 2. Okay? So substituting, so there is no t here, so this will be just a constant. Therefore, if this is your normal vector, then this will be your A, this will be your B, this will be your C. for your, I found the oscillating plane pala, no? It should be the normal plane. That is why I'm confused. Sorry. So for the oscillating plane, this will be equal to, we have A here is 1 over square root of 2, right? And then we have x minus x dot, we have 0. And then plus, we have 0 here. And then y minus y sub 0, which is 1. I'll just make this red now, just to make things obvious that this is substituted. So 0, and then we have 0 here. This would be 1. Plus, we have 1 over the square root of 2. Then we have z minus pi over 2 is equal to 0. So simplifying this, we have x over square root of 2. This will be cancelled out to 0, plus this will be z over the square root of 2 minus pi over 2 square root of 2 is equal to 0. So you can see we can actually factor out this square root of 2, no? Or we can remove the square root of 2, so that we have x plus z is equal to negative pi over 2, right? Is equal to 0. Therefore, this is your curve already, no? So this will be your equation, sorry, not plus, but x plus z. So this will be your equation of your plane. That is the oscillating plane. Now for the normal plane, we have to do this again, no? So the normal plane is normal to the unit tangent vector t prime of t, t of t lang pala, no? So your n here, your n vector should be equal to this unit tangent vector. So what is our unit tangent vector for this previous problem? We have this, right? So negative sine t cos t. Sorry. So we have a negative sine t over square root of 2, and then cos t over square root of 2. So I'll just take a note here now from previous problem. Problem. Forget to take note of this one and this one. And then we have 1 over square root of 2 for this one. So therefore your A here, if sorry, not yet now. So when we substitute pi over 2 for this one, we have to solve this again, right? So we have negative, so it's negative 1 over square root of 2. And then this will be 0. This will be 1 over square root of 2. Okay. So this will be your normal vector. So therefore, this will be your A, this will be your B, this will be your C. So again, going again with the formula, we have this. So we have the same point. So 1 over square root of 2. And then multiplied by x minus 0. And then plus 0, y minus 1. And then plus, we have 1 over square root of 2, z minus pi over 2, right? So pi over 2 is equal to 0. So substituting at this, simplifying this, okay, we can cancel out this. Substituting this, we have negative x over square root of 2 plus z square root of 2 over square root of 2 minus pi over 2 square root of 2. So again, we can cancel out, or we can factor out the square root of 2 to cancel that out. So since this is a common denominator of these three terms, we can just multiply this by square root of 2, so that this will vanish, multiplying 0 to square root of 2. This will be negative x plus z minus pi over 2 is equal to 0. Okay. So that's it. This will be your equation of your normal plane. Yeah. Okay. Okay, that's all. So, for the last topic for normal and binormal vectors is the torsion. So the torsion is another concept that is similar with curvature. So if curvature is its deviation from the straight line, the torsion is the amount of twist. No, you can imagine how does it twist through the what? No, through the binormal vector or this binormal vector. So the torsion is equal to or the torsion function, which is tau, is equal to negative the derivative of the binormal vector dot product of the normal vector over the length of the first derivative of your vector value function. So let's just have an example to find the torsion of a helix. Okay, so this is the same problem again now. So this is the same problem over and over again. So from previous problem, okay, from previous problem, we already have the values already, so that we won't compute this all over again. To find the torsion, which is tau of t, this is equal to negative the binormal vector or the first derivative of the binormal vector, the dot product and the dot product of the normal vector all over the length of your r prime of t. Ayan. So what is this? We already solved this. Not yet, right? But we know the b vector, the binormal vector. So this is the binormal vector. Okay, so you can list down the given. Okay, I cannot. Why can't I sorry. So the binormal vector, so from previous problem, no? From previous, so we have binormal vector. This is equal to okay, sine t negative cosine. So sine t over square root of 2 and then negative cosine t over square root of 2 and then 1 over square root of 2. Okay, what's next? So we have the normal vector as well. So the normal vector, we have, where is it? Oh, not here. So the normal vector is here. Okay. So negative cos t sine t. Sorry, not that far. We have negative cos t, and then we have negative sine t, and then 0. Yeah. And then r prime of t, we have here r prime of t. So r prime of t is this. Yeah. So negative sine t cos t 1. Negative sine t cos t 1. This is your r prime of t. Okay. So already have this as our given. We can solve for the first derivative of the binormal vector. So for the binormal vector derivative, we have here negative cos t over square root of 2. And then we have negative, sorry, this should be positive. Oh no. And then negative sine or negative of negative sine. So this will become sine t over the square root of 2. And then this will be 0. And then for the normal vectors, is it the derivative? It will be the derivative. And then the length of r prime of t. We're not writing the vector anymore. Okay, so this will be the square root of the sum of the squares. So we have negative sine t squared plus we have cosine t squared plus 1 squared. Okay. So this will be equal to again 1 plus 1, which is square root of 2. So therefore that the tau it is a little bit tricky to write. It could be the unit tangent vector. So the tau will be equal to the negative of the dot product of these two vectors. So the dot product is just the cross multiplication, sorry, the entry-wise multiplication of these two. So we have cosine squared t over the square root of 2, and then plus, so entry-wise now, so we have plus negative sine squared t over 2, right? And then plus, so entry-wise we have 0 here. 0 times 0 is 0. Then what's next? Over the square root of 2. So this will be equal to what? Actually, we can simplify this as, we can factor this out, no? The negative, it should be square root. The negative and the 1 over square root of 2. So we have negative 1 over square root of 2. And then we have cosine squared t plus sine squared t, right? Okay, so right. And then over the square root of 2. So we know that this is equal to 1. So this will become, so can we cancel this out? Okay, not actually. So 1 over square root of 2 times square root of 2 actually, you know. So what about the negative sign? We forgot the negative sign here. Sorry. There should be a negative sign outside. So this will cancel out pala, no? So this will cancel out. Then negative here pala and then negative here. So you can cancel out this negative sign. So therefore, 1 over square root of 2 times square root of 2. So basically, this is just square root of 2 times 2 inside. So this will be 1 over 2. So the torsion of your helix will be a constant 1/2. So what does that mean? So visually, you can imagine comparing this to a circle. If this is a circle, the torsion is actually 0. And a helix, okay, the torsion is 1/2. So what does that mean? So the circle is not twisting, no? It is not twisting. That is similar to twisting something, no? But a helix has this twist, a deviation actually from the oscillating plane. You can imagine that. The oscillating plane, no? It is deviating from the oscillating. Okay. So that's it for torsion. And see you guys next video. I'll just add this. Now you can find the torsion directly in terms of just the derivatives of your vector valued function R. So instead of calculating this long the binormal and normal vectors, we can just do this directly by finding the derivatives of your R and then evaluating its dot product and cross product and so on. Okay, so that's it. Thank you guys.